So we have calculated statistics for the state of New York and for other states. And now we're going to start digging in and looking at these statistics, visualizing it to understand what's going on. Okay. So the first step, as always, is to read in the data. So we read in the weather data, which is basically for each station, year, and measurement. We have a list of 365 values. And we read the statistics, which is basically a collection of various statistics, including eigenvectors, eigenvalues, mean, percentiles, top 1%, bottom 1%, top 0.1%, bottom 0.1%, a sample of the values, and the number of entries that are not defined, then the mean value. Okay, so basically all of those we calculated in a previous notebook, and we have them ready for us to analyze. Then we're going to read information about the station, the stations, and we're going to join it with this information. So we're going to get this joint data frame, which has basically for each station measurement, year, and the values also has the values that are associated with that station. So distance to coast, latitude, longitude, elevation, which state it is, and the name of the station. Okay. So the first thing we're going to do after registering this data frame as a table in SQL Spark is to select to look within these stations, which stations have the most measurements. Okay, so this SQL query here selects the name and the count of name from this table, JDF, and we group it by name and we order it by count. And we do it descending. Okay, so the first station here is the station that has 719 measurements across all of the different measurements and all of the years. So that gives us a sense about how dense is our data. Okay. So to look a little bit further, using this query, we can find how many measurements of each type for a particular station. So we choose here a station called Elmira, which is one of the stations that has a lot of measurements. And we see that for the 6 measurements, we have about 100 years each. Okay, so we have 100 years of measurements for each one of them. But that doesn't necessarily mean that they're all on the same year. So we might want to also check which years we have with all 6 measurements. Okay, so this is 1924, 1977, 1990. For this station, you have the full array of measurements. And in general, we try to identify which are the parts of the data which are dense, for which we have a lot of data, so we can draw statistical conclusions. Okay, so now we're going to transform what we have to a pandas data frame that is easier for visualization. And what this is basically that we're selecting a station and a year, and we're taking all of the entries for those and making them into a pandas data frame. And here it is. Here's the pandas data frame in front of us. So let's start to do some plots. Okay, so one thing we can do is we can explicitly use matplotlib commands and get a plot, and that basically what we see here is the T max, T minimum, and T observed for a particular station on a particular year, Elmira at 2007. And we see that the max, not surprisingly, is at the top, and the min is at the bottom, and the T observed is somewhere in the middle. T observed is the temperature measured at noon. Okay, so as we'll see, T observed is a more reliable measure than Tmax and Tmin. Okay, so one little thing that we didn't have in the plot we did is to show the x-axis in terms of the actual months. Okay, so it's useful to not have the x-axis be just 100 and 365, but to go from January, April, July, August, and then when we look at it, we know, oh, this makes sense because July is in general the hottest month. Okay, so the measurements here also are in terms of Celsius, degrees Celsius. Okay, so we have a sense of how a particular one looks, and we can look at 10 or 100. But once we get to looking at 100 graphs, it's basically data. It's too much data for us to actually observe. So we need to start thinking about how to summarize it. But before we summarize, we really want to see where are we missing values. So let's look at that. So the coming plots basically show us for different measurements how many elements are measured. So this initially might seem a very scary kind of plot, like there's a lot of missing things, but in fact this is the number of good measurements, and you see that the variation is only between 12,300 and 12,600. So really it's we get a pretty constant number of measurements, but there are some definitely fluctuations. This is for Tmin and Tmax. This is for T observed and precipitation. And here we have it for snow and snow depth. And one of the things that is kind of interesting that we can see in this one is that still the fluctuations are not really that big, but they are definitely man-made, right? Because what you see here as steps is exactly at the end, at the boundary between 2 months. Okay, so in October you have this jump and so on. And it has probably something to do with the way that this data was collected on a monthly basis or so on. And if you think about what was collected, here we have snow and here we have snow depth. So it's kind of curious that that in terms of snow, we have very few, we have fewer measurements in the summer, and in terms of snow depth, we have more. I mean, what is pretty clear is that in July, all of these measurements were 0. So maybe different stations had different approaches to doing that, and some stations said, okay, well, it's a summer, obviously there is nothing, let me just not put any entry rather than put the entry 0. So that might explain this. So we're looking at it, and basically we want to see that the number of measurements that we have for each day are comparable, and they are, and so we can continue, we can go on. Sometimes, as we'll see, the measurements for some things are much more than for other things, and then we need to take that into account. Okay, so let's look at the next level, which is the mean and standard deviation of the observations. So what we see here is the minimum plus minus standard deviation for Tmin, and this is for Tmax. So the orange line is the mean, and then we add to it the standard deviation for each time. And you see that for temperature, there is a slightly larger deviation in the winter, and slightly less deviation in the summer, but it's not really a very big difference. What we see here is that in this particular day, we have a very high variance, and that's probably because there was some kind of outlier. Okay, so there was some measurement that just doesn't really fit, and so it creates a very high standard deviation. Okay, here we see the T observed, and here we see precipitation. So with precipitation, it's kind of interesting. What we see is that it's really pretty constant throughout the year in terms of the average precipitation that New York gets. I mean, it gets it in terms of snow in the winter and rain in the summer, but the amount is more or less the same. And the standard deviation is kind of higher in the summer, right? In the winter, it's more the standard deviation is smaller than in the summer. But in general, if you just look at the average, you see that there is very little variation as a function of time. So here is T observed again, and here we see the snow and snow depth. So the left-hand graph tells us how much snow fell, and we see that it's not surprising that snow falls mostly or only in the winter, let's say January, February, March, and at the end after October, September, November, December. Okay, so that's when snow falls, and in the middle of the year, during the summer, there is basically no snow unless this measurement is real. But probably it is just some error in the measurement. But overall, this is still very noisy. If we compare it to the to the graph of the the depth of the snow is much smoother. Okay, so the depth of the snow is a smoother graph, and that makes sense because snow depth doesn't change abruptly from day to day. It's basically the integral of this snowfall. So as we'll see, this one is much easier to analyze and understand than the others. Okay, so we'll stop here, and in the next video, we're going to talk about plotting percentage of variance against the eigenvectors. See you then.